Hello guys, welcome back to differentiation. Now we are already in the topic of chapter 16 about rates of change. So for today's session, we will learn about the constant rate and define it with the variable rate of change. Okay, let's begin with the learning objective. In this chapter, you will learn to solve problems involving rate of change. And then later, we'll also apply the chain rule to solve problems involving connected rates of change. So before having the example, let's review. We already know that the first derivative dy dx is the rate of change of y with respect to x. The variable is x, right? So if we change the first derivative become dy dt, so it will be the rate of change of y with respect to t. In here, t is time. So later, the rate of change compared to the time is mostly used and said to be the rate of change or only the rate. Let's begin with example 1. The radius r centimeter of a circle changes with time t second, and they are related by the equation r equals 0.5t plus 1.5. Find the initial value of r and the rate of change of r. And then later we'll also sketch the RT graph and describe the relationship between r and t. Okay, for initial value of r, we'll substitute t equals what? Yes, we'll substitute t equals 0, and here we have the radius is 1.5 centimeter. Let's find out the rate of change of r. So for the rate of change of r, it will be dr dt. So dr dt from here will have 0.5t, right? T is with the power of 1 and 0.5 is multiplied with 1, and then the power of t becomes 0. Or you already know also the partial case of t equals 1 to become a constant. And then 1.5 is gone here. So r increases at a constant rate of 0.5 centimeter per second. Let's see the sketch of the RT graph. Here, you can see that r and t will be linearly related. So the radius is a line compared to the time, and the rate of change of r with respect to time is the gradient of the line. You can see that for this linear line, the gradient will be a constant, or the value is 0.5 earlier. So in general, we can conclude that if a variable x is linearly related to the time t, then x is symbolized as mt plus c. Here you can see that the power of t is 1. Then when you have dx dt, what you will have is the gradient, or the value is m. Here, x is said to change at a constant rate or steady rate. Let's compare with this example 2. In here, we have the volume v liters of water in a tank after t seconds, which is given by this function f equals 5 minus 2 over t plus 1. We'll find the rate of volume during the interval t equals 2 to t equals 2.1, and then we'll find the rate of volume at the instant t equals 3. Okay, so for the A part, when t equals 2, then v, the first v is 4 and 1/3. And then when t equals 2.1, we can calculate then the v is 4, 11, and 31. We will calculate the changes of v compared to the changes of time, which is delta v over delta t. So because it is very small, the symbol is using dou v over dou t, or this is actually the same with delta v over delta t. So here we calculate v2 minus v1 divided by t2 minus t1. So it is 0.215. Then here, rate of volume during the interval t equals 2 to t equals 2.1 will be 0.215 liter per second. So if we compare with the B part, in here, what we have is the rate of volume at the instant t equals 3. So we recalling our dvdt, which is actually the changes of v compared to the changes of time when time is very small. So we use dvdt and differentiate v with respect to time. We change the v function become 5 minus 2 times t plus 1 to the power of negative 1, and dvdt become 2 over t plus 1 square, right? Then when you substitute t is 3, dvdt become 2 over 3 plus 1 square, and we can simplify dvdt become 1 over 8. So here the volume of water is increasing at the rate of 1 over 8 liter per second at this instant. In here we can see that dvdt will be a variable. So when a variable x varies with time t, then we can have x, which is a function of t, differentiated become dx dt. In here, we can say that the rate of change of x with respect to time at any instant t can be calculated using the differentiation, and we can substitute the instant t so that we have the rate. So later, when the rate is positive, it means the rate is increasing, and when dx dt is negative, it means the changes is decreasing. That's all for this session. We will continue again with other example and the discussion in class. See you later. Stay healthy and God bless you all. Bye bye.